represents powers, how many powers of 10 you have for each position, right? 10 options. Each one of these is some power of 10. Why do humans use base 10? Why do humans use base 10? There's nothing wrong with when you were born, us telling you, hey, we only have 8 options. Okay, 8 options, and each one of these are powers of 8, not powers of 10. Why 10? There's a reason. We're not moving on until y'all figure it out. Why 10 options? Why 10 digits? Why not 8? Why not 6? Why not 15? There you go. What is it? We have 10 freaking fingers. Okay? It's the way we count, right? We have 10 fingers. If we had 8 fingers, I bet my life on it that we would be using a base 8 number system. There's nothing special about base 10. To us, it's special because we have 10 fingers. That's really it. That's really it. For us, base 10 seems perfect, doesn't it? Because we have 10 fingers. But again, it only seems perfect because this is what you were taught from childhood. This is what makes sense to you. If we had 12 fingers, okay, let's say we had 12 fingers, we would be in a number system where we would have 2 other symbols here that you have never seen before, right? Like right now, when we look at that number 4, it just looks like the number frickin' 4, right? But it's just a symbol, right? If I had some other, there it is. Okay, I just made that up. Now it looks crazy to you, but in my world of 12 fingers, that looks like a 4. Like the 4 looks to you, that symbol looks like to me. That makes sense? And then I can have another symbol over here. I don't know, there it is, right? It looks foreign to you, but now what would happen is this. For each of these digits, I could put how many options in here now? There's 12 options. And whatever that first one is, that's how many what? How many what to the zeros? How many what to the ones? 12 to the 0, 12 to the 1, 12 to the, you see? Everything would be base 12 to me. All right? So now let's talk about another system. Base 10 is important to us. It's an important exponential function because everything we do as humans is base 10. Our number system is base 10. But not everything in our world works in base 10. Computers work in what base system? Do you all know what base? Base 2. Because a computer only knows what? Off and on. That's it. Off and on. I'm going to make you dizzy. Right? That's all a computer knows. There either is a signal or there is not a signal, electrical signal. The signal's there or it's not. 0, 1. 0, 1. 0, no signal. 1, signal. That's called binary. Binary meaning 2, right? Base 2. So I'm going to show you right now. This is worth it. I think this is worth it for us to discover this. So when we look at the base 2 number system, base 2. Now, so imagine you're like some alien world, okay? Base 2. That means that there's only 2 options. There's only when you go to write a number, right? When you go to write a number, you only have 2 options that you can put in there. And the 2 options we're going to use are symbols you recognize, 0 and 1, right? 0 and 1. Those are the 2 symbols that you're allowed to put in there. So someone give me a symbol to put here. 1. Here? 0? 0? Let's do one more. 1. Okay, there you go. What number is that? for us as humans, right, if we look at that, we say that's 1001, right? We say that's 1001 in base 10. But I'm saying this is a base 2 number. So what it means is that this is 1 what? 1, how many options do we have? 2. So this is how many 2 to the zeros we have. This one would be plus, what, 0, 2 to the ones. This one would be plus 0, 2 to the third. Oh, sorry, squared, yes. Lost track. And then this last one would be, we have 1, 2 to the third. So what is 2 to the third for us? What's 2 to the third in base 10? 8, right? So this would be 8. We have 1 8, so that's 8. And then this is 0. That's 0. And then what's 2 to the 0 for us? 1. 1 times 1? 1. So plus 1. So what is this number? 9. The number 1001 in binary is 1001. In base 10, it's the number 9. So if I go to my keyboard and I hit 9, this is what the computer sees. It sees 1s and 0s only. Okay. Sorry. Anyway, base 10 is important to us because we have 10 fingers, right? Computers, have you all heard of hexadecimal before? Hexadecimal, you all know what base that is? 16. 16. So it's their digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then they go A, B, C, D. They start using letters. All right, I can keep going on this, all right? I can keep, but I'm not going to because we have to at some point continue moving the train down the road. Hopefully I've at least convinced you why this one's important, because it's unique to the human experience, right? I think it'd be awesome if like some alien species came down, right? And they had 8 fingers and they were all base 8, right? That'd be pretty cool. And then it would be very surprising if they weren't, right? Like why would they do base 10? Like there's nothing special about any base. Every base is pretty much the same ideas. All right, base E. We need to talk about this. E. How many of y'all have seen that letter before? E. Y'all know what it is? Y'all know what it is? Do y'all know what pi is? Y'all seen pi before, right? What's the unique thing about pi? It's never-ending decimal, so 3.1415, and it keeps going, right? And it keeps going. There's no pattern, so it doesn't start repeating itself ever, and it goes forever. This is what we call a non-repeating, non-terminating decimal. Those numbers are called irrational numbers. I know I've talked about this earlier in the class, irrational, right? That's an irrational number. Well, there's another number that's irrational, and it's E. And E is approximately 2.718. And again, it goes on forever. It never repeats. It never stops. Anytime we have a special number, a very special number in math, we usually represent it with a letter, if it's special. Pi is special because when you look at a circle, right, and you take the diameter and you look at the circumference of a circle, the circumference is always pi times the diameter. Let me put D instead of capital D. You probably are familiar with this formula, 2 pi r. Circumference is 2 pi r. But what's twice the radius? What's twice the radius? The diameter. So this is a more simple formula. And you can take this formula and you can solve it for pi. Divide both sides by D. So if someone were to ask you, hey, what is pi? You just say, hey, take any circle, take the circumference and divide by the diameter. That's what pi is. It's a very simple definition for pi. But E is a lot harder to explain what it is, all right? It is a lot harder. E is named after the mathematician who discovered the number. His name's Euler. Actually spelled E-U-L-E-R. Euler. But I think it was German. I could be wrong. 1700s, I believe, 1800s. He discovered E. Now, as easy as it is for me to explain what pi is, as in terms of just a simple ratio on a circle, it's not so simple to explain what E is. In fact, I'm going to define what E is to my Cal 2 class next class. We are going to actually define explicitly what E is. And in Cal 1 we do it as well. But for us, I'm just going to write down one of the definitions for you, okay? And you're going to look at it and go, what? And don't worry about it, all right? If you want a precise definition for what E is equal to, let's see, there's a couple of definitions. You want the Cal 1 or the Cal 2 version?
Cal 1.
You want Cal 1? I'll give you both. Here's the Cal 1 version. E is the limit as n goes to infinity of 1 plus 1 over n raised to the n. That's what E is. It won't make a lot of sense to you, but that's what it is. All right? And then the other definition from Cal 2 is that E to the first power, or E is 1 plus 1 over 2 plus 1 over 2, how do I want to do this for you? I'll do it this way. 1 I don't know if y'all have ever seen that before. Y'all know what this is? No? It's called factorial. So don't worry about it. I'm just going to write it down, okay? Forever. That never stops. It goes forever. So those are two definitions of E. And right now you're looking at them going, okay, whatever you say, right? It's not as simple as pi. But what I'm here to try to tell you is that this number E is extremely important in mathematics. Would y'all like me to explain, because it's in Cal 1, which is only, what, 2 classes away from here? Would y'all like me to try and explain what makes it so special? Yes? I can do it geometrically. I can't explain the number, like why this number, I can't explain that part, but what I can do is show you what makes it so awesome, all right? Okay, so here's the way I'm going to try and explain it. Y'all know what a line is, right? And y'all know what a slope of a line is, yes? Okay, so here's what mathematicians were doing. We were looking for a function, right? We were like, hey, I wonder if there's a function out there that does this. That when you look at the function, if you go and let me graph it, okay? Let me graph this. So mathematicians were like, hey, I wonder if there's a function that when you go to the function, let me give you this particular example, x squared. Let me get rid of this. I think this will be easier for us. We all know what that looks like, right? X squared. So we were like, hey, I wonder if, like, when I go to, let's see, when I go to 2, what does this function spit out? 4. Okay, right? We're all good with that. So mathematicians were like, hey, I wonder if we can find a function. Is there a yardstick in here? There's not. I've asked that before, haven't I? I wonder if there's a function that when I go to this point 2 and I get the value 4, that if you create a line that goes through that point and is tangent to the curve, meaning it just touches the curve at a single point. Like not like this, not like that, just barely touching through that point. We call that a tangent line. Okay, do y'all see the concept of a tangent line? The question was, I wonder if there's a function out there that when you look at the slope of this tangent line, it's equal to that value right there. It's equal to the height of the function. So does that slope look positive to you? The slope of that line? It's positive? Do you think that the slope of that line is 4? It does turn out that for this particular function right now, this slope is 4. You're just going to have to trust me on that. So do you see, if you trust me, the slope of this line is 4, and that's also equal to the value of the function there, all right? But if you move to another point like 3, what's the value of the function here? 9. And now you go find that tangent line there, and you look for its slope. Guess what? It's not 9. It's 6. And you'll have to trust me. It would be nice if it was 9, because then the slope would always be equal to this value. So we were looking, is there a function that does that? Is there a function that for any point you go to, you go up to the graph, whatever that value that comes out is equal to the slope of the tangent line for every point on the graph? Does that make any sense at all to you? Yeah. And we were looking everywhere for this function, trying to find it. Didn't even know if it existed. And we looked and looked and looked and looked and looked and looked, and we found it, finally. And it's this function here, e to the x. It is unique. It is the only one in the universe that does that, and we can't explain why it's that number that makes it happen, but it does. It just kind of naturally occurs that this is the one, right? So we call it the natural exponential function because it just naturally occurs, just like the sky is blue. Why? Because sky, well, there's reasons why the sky is blue, but I'm just saying that's a natural occurrence on this planet, right? Leaves on a tree are green. Why? Because they just are, right? This is the function that behaves that way. Why? Because it just does, all right?
So is E always repeating like pi, or is it?
Yes, E always repeats like pi, which is very strange, because how can you take a number that repeats like pi and then raise it to a power? Well, you're going to have to do an approximation, aren't you? Yeah, at some point you'll have to do an approximation. Okay. How are we doing? 15 minutes. So let's see what the graph of this looks like, all right? Let's see what the graph of this looks like. So first of all, what can you tell me about the growth? Is it exponential growth or decay? That function. Growth, because what's E? About 2.7 something, which is bigger than 1. So I know this must go through the point 0, 1, right? And I know it's going to grow like that. Now, to figure out exactly what it does, I would have to make a table and start plugging some values in. 0, get 1, plug in 1. What's e to the first power? So this is where you need your calculators. You're going to get approximately 2.718. Now, on your calculator, you should have an e key. You should have a key on there. Do not confuse that with this e. You know how we just got an e when we were doing that big long number for the federal deficit? That's a different e. That's like a block e. That's more of a script e. This means like scientific notation. That e is the what we call the natural base. Did you all get e to the first power is 2.718?
Yeah.
Okay, now plug in 2. E squared, about 7.39. Go one more, e cubed. 20.08, something like that. Now we would just estimate this, right? I mean, we can't plot these decimals accurately. So if we go out 1 to the right, we're going to go up to, we're going to go almost to 3. And then we plug in 2, and we're at 7. So that's, I think I'm off my chart here. It's exponential growth. And then to the left, we know it decays down and has a horizontal asymptote. And again, this function, I mean, let's look at the projector. I want to show it to you. This is such an important function. In Cal 1, you'll learn that this function is the only function that is its own derivative. That's the end result that we'll come up with in Cal 1. It's like, this is the only function that is its own derivative. All right, I'm going to project the graph of this. Come on, what's going on? Is this room 219? Yeah, 219. Why is it not connecting wirelessly? No, didn't like that. Okay, there we go. All right, so here we go. I'm going to go to Desmos and graph this. I'm going to do it up here. So let's first do y equals 2 to the x. No, not 2 to the 2. 2 to the x. Okay, that's 2 to the x. And now let's do 10 to the x. Ooh, that grows real fast. And now let's do e to the x. And if you type e to the x, Desmos knows what e is, obviously. All right, so the green one is, I need to make this square, hold on. So, yeah. So the green one is the exponential function e to the x, the green one. So let me see if I can again try and explain that Cal 1 concept. If I were to go to, let's say, let's go to the red function right here. That red function, let's go to 1. And I'm going to put a little line there, okay? That function right there, the slope of that line is not equal to 2. It's not. Promise you, it's not. If I go to the green one, though, at 1, if I go to the green one to that point right there, that slope of that line, guess what it is? Whatever that y value is. What's that y value? At 1, where were we? 2.7. So the slope of that line is 2.718. How about right here? At 0, go up here. Slope of that green, I'm looking at the green one. What's the slope of that line? 1. How do I know? Because that's the value of that function at 0 is 1. See, this is the only function where these values are equal to the slope of the tangent line at that point. No other graph does that, just that one. All right.
Could transformations work on that or no?
In terms of the slope of the tangent line, you can move it up and down, but that's it. You can't move it left or right, then you lose it.
I meant like stretches.
Stretches won't, you'll lose it. All right, that's all I wanted to show you on that. So where are we going with this? Oh, we have one last little thing we want to do. We're going to get more into this exponential function later. What we're going to end with here is we're going to try and just solve some simple equations. So we're kind of going to shift gears here in this last 9 minutes. We're going to shift gears. And I want us to solve some equations. Solving equations involving exponents. All right, so I want you to look at this equation. X cubed equals 8. Can you solve that equation? Can you tell me what number I cubed to get 8? You can probably do it just by thinking, right? 2? 2 cubed? You could do cube root on each side. So here x would be 2. Check, just by looking, right? We know how to solve equations like this. But how about if I change it? And instead of giving you that, I give you this. That's different, right? Where's the variable that I'm asking you to solve for? It's in the exponent, right? It's in the exponent. Well, not easy, is it? That's not easy, generally speaking. That's not an easy thing to do. What I want you to see here is the position change of the x. When it was in the base, we've solved equations like that in our life before. But when have we ever solved equations where the exponent's up in the top? A little harder, right? Let me give you another one. So right now, this is a question mark. We don't know. How about this one? How about that? That's not an equation that you've seen before, right? Or maybe you have, but not in this class. Right? I'm asking you what value of x you plug into this to make this whole thing true. See, it's not a linear equation. It's not a quadratic equation. It's not a rational equation. Nothing that you have in your arsenal will equip you to do this, right? Don't know. Don't know how to do this. We will, okay? By the end of next class. Well, maybe. Next class we'll be able to do it. I'm just trying to give you kind of the preview of what we're going to have to bring in the inverses. But all right, so how about this one? 4 to the x equals 16. Can you solve that one?
Yes.
I made it special for you, right? Made it special because that one you could actually think of the answer, couldn't you? 4 squared is 16.
Is there a way to isolate x?
Well, no, there's not a way to isolate x. This is just us realizing that the x needs to be 2, right? What you could do is this, though. You could rewrite 16 as 4 squared, right? And then you could say, all right, look, for these two to be equal, since they have the same base, that means this obviously needs to be equal to that, right? So then x must be 2. That's not a bad technique, right? It's not a bad technique. How about this one? How about 2 to the x minus 3 equals 8?
2x minus 3 equals 2 cubed.
So you realize that 8 is a power of 2, right? So you can rewrite this as 2 to the x minus 3 equals 2 to the third. And that means that this must be equal to this. So write that down. And now to solve that, and you get x is 6. And you can check it. 6 minus 3? 3. 2 cubed? 8. I want to give you another one. How about 5 to the 6 minus 2x minus 25, minus 20 equals 80. Hold on. Sorry, 105. There we go. Okay, look at that. That looks insane, right? Doesn't it? Like, what's x? Right? What's x? So these two that I did, the thing that made these doable is the fact that I could tell that 16 is a power of 4, and I could tell that 8 is a power of 2, right? But here, I have 5 here, right? My variable's here. The only way this is going to work is if somehow this is a power of 5. Is it? Add 20 to both sides. Is 125 a power of 5? Yeah, it's 5 cubed. 5 times 5 times 5. Right? What's 5 times 5? 25? What's 5 25s? Or what's 5 quarters? Who uses quarters? Anyone use money anymore?
I do it a lot.
Yeah, you have money? Okay. So I could rewrite this as 5 to the 6 minus 2x equals what? What? 5 to the third power. You see, now I've got them both to 5s on the base. And that means that the two exponents must be equal to one another. So write that down. 6 minus 2x equals 3. And then solve that for, subtract 6, negative 4, right? Divide by negative 2. X is 2. Of course the x is 2, right? Let's check it. Let's just check our answer. If x is 2, what's 2 times 2? 4. 6 minus 4? 2, right? 5 squared? Wait a minute, hold on. Was our answer 2? What's going on here?
That's what I said, it's 4.5, because it would be 3. 6 minus 3.
What did I do? 6 minus 2x. What? Where? What the hell did I do? I had, what was this supposed to be? That was a complete brain fart. What is this next line supposed to be? Subtract 6, right? Negative 3. Right? Negative 3. I put negative 4, didn't I?
Yeah.
I don't know why I did that. And now divide both sides by negative 2 and you get 3 over 2. That's going to be harder to check, maybe. No, it'll work. That's our answer, 3 halves.
And you're multiplying it by 2.
So what's 2 times 3 halves?
3.
The 3, 6 minus 3, 3, 5 cubed, 125, take away 20. It works. It works. So this system that we're using here to try and solve this, it works sometimes, other times it doesn't. Yes? Yeah, I'll take that at the end. Yeah. Oh, man. I remembered. Someone's ready to turn them in. How are we doing here? So I would like for you to attempt the homework. Attempt the homework for 6.3. I think what you'll see is that there will be things in there that look familiar. There'll be other things that I didn't really emphasize too much. Do what you can. Don't stress out about it. Do what you can on it. I've presented, I think, the most important concepts. We come back next time. We start logarithmic functions. And then we're going to have a way of solving these. All of these problems that I have up here, we'll have a way of doing it on our calculators. All right? Okay, if you have your quiz, just leave it right here on the way out. And have a good day. We'll see you on Thursday. Can you put it on the corner right there? Thank you. Yes.
So I'm at 78 right now.
Hold on. I'm still recording, so.